in order to finally put this topic and its difficulty to rest, I've decided to show my actual real workbook, which I use for the lectures. And I will elucidate, I'll show you how to go about electrochemical calculations at A levels. This is what we denote as atomic weight of single elements like silver, gold, copper, tungsten, nickel, any single element, it'll be A. Z would always be charge. Z is the valency. And then you also need to know how to calculate the oxidation, overall oxidation charge of a compound before you apply the Z. This is the first formula, PV equals nRT, then V equals number of moles times 8.13 times temperature. So PV is Boyle's law, and you can also substitute it, and then you can use this one as well, nRT over P equals 1 over volume. No, not 1 over volume, sorry. It'll be nRT over P equals volume. And volume can further be broken down into, if we're talking about the volume of a gas or a liquid, we can dissociate it into molecular mass of the gas or liquid times the number of moles involved divided by the density of the gas or liquid. So that's how we can get it, okay? Sometimes they'll ask you about the density by providing you these three. They'll ask you for this, and you'll be like, how am I supposed to do this? I don't even know. I was never taught this, but this is how you do it. You have to substitute and counter substitute all of these formulae in order to get there. That's the first one. Mass deposited, okay? Current passed for amount of time multiplied by the relative atomic mass of the element under question, silver, nickel, copper, iron, whatever, divided by the Faraday amount, molar amount, constant 96,500, divided by the valency of the element metal in question. For silver, it'll be 1, gold, it'll be 2, copper 1 or 2, and carbon, it would be minus 4, and then platinum, it would be also plus 2. Plus 1 for and then so on and so forth. You have to make sure you put the correct valency. The volume of the gas released would be Q. This is actually Q. I've simplified it for you. It's supposed to be Q, charge passed. So they don't tell you charge passed. They tell you this much current was there and it was passed for 10 minutes. You have to dissociate the 10 minutes into seconds, which is 600 seconds. So, and then you have at RTP, it would be 11.2 divided by the valency, not 12. And at STP, it would be so at RTP, it would be 12 divided by 2 divided by the valency, and then at STP, it would be 11.2 divided by the valency. And then the third formula is the Faraday constant, which is Q over the Faraday constant. And then F equals Q over the Faraday constant, and then you have F equals NE, and each E is 1.69 times 10 to the power minus 19 coulombs. Okay, and then you have to remember oil oxidation is loss of electrons, loss of oxygen, loss of hydrogen, addition of oxygen, and reduction is gain of hydrogen, gain of electrons, gain, and then loss of oxygen. Oxidizing agents oxidized by getting reduced in the process, and vice versa. Reducing agents, reductants, they reduce by getting oxidized in the process. So anions, they become anions by gaining an electron. So they get reduced. Anions are reduced originally, and then cations are oxidized originally. But when cations go to the cathode, they become reduced, and anions become oxidized. So a little bit of an opposite tattletale takes place. The volume of gas released will be Q over F times 11.2 over the valency. Yes, please take screenshots. Next, this is charge IT equals number of electrons passed times the Faraday constant, which is 96,500. This is Q equals IT, current times time. This is mass deposited, which is IT times the atomic mass of the metal, divided by the Faraday constant, 96,500, times the valency of the metal in question. Do not get this wrong, otherwise the whole answer can be shifted by 1 or 2 magnitudes. This is the volume of gas released at either cathode or anode, 96,500 times 12 divided by, IT, which is current times time, times 12 divided by Faraday constant times the valency. Okay, so this 12 is only 12 when it's a room temperature pressure, but if it's STP, it'll be 11.2. It's obvious 12 is half of 24, which we use 24 decimeter cubed in molar gas calculations, but here we use 12 for a specific reason. Why? Because these molecules, they get split into nascent atoms, and each atom is half then of the molecule, and that's why we use 12, not 24, 11.2, not 22.4. Okay, right? So volume of gas released at the cathode or anode under STP, it would be IT times 11.2 divided by 96,500 times valency. Okay, so cathodic deposition, anodic deposition, anodic release of gas release at anode, gas release at cathode, cathodic deposition. Remember this. In the electrochemical series, there's a preferential discharge. Not all elements of metals or gases will release at the same time on cathode. There'll be a preferential sequence, and some compounds they never dissociate because they're too tightly bonded. Nitrates, carbonates, phosphates, they never do that. They never dissociate. They stay within the solution because their internal intra-atomic, intramolecular bonding forces are far more stronger than the current passing through. Oxidation is loss of electrons, loss of hydrogen, gain of oxygen. Reduction is loss of oxygen, gain of hydrogen, gain of electrons. So anions, originally, they become reduced to become an anion, and cations, they become oxidized to become a cation. But when they go to their respective anodes and cathodes, the opposite happens to them. Anions become oxidized, they lose the extra electrons, and cations, they gain the deficient electrons. So get cations at cathode get reduced, anions at anode get oxidized. Okay, so it's known as anodic oxidation, cathodic reduction. Just understand that oxidizing agents oxidize the subject or the substrate by getting reduced in the process. Reductants or reducing agents, they reduce the substrate by getting oxidized in the process. This is the circuitry measurements, and there's supposed to be a stopwatch in the circuit as well. And then cathode, anode, electrolyte solution, casing, industrial casing, right? That's that. Atomic weight, molecular mass, atomic mass, then the charge, which is valency, oxidation number, calculation dependent charge valency. Okay, so this is reduction. Reduction is gain. Reduction is gain, which takes place at the cathode. Cathodic reduction, anodic oxidation. So yeah. And here's some questions. Milliamps. So it'll be 10. This is how you have to convert every single time into seconds. It has to be seconds. It can't be hours or minutes. This is how you do it. You dissociate the equation, KCl. So 0.45 moles of This is how you do it. Cackle 2, you dissociate it into 1 mole of calcium, 2 moles of oxygen, chlorine. Molten aluminium oxide would be Al2O3, so 3 moles of aluminium, 2 moles of oxygen, single nascent oxygen. Lead bromide would be each 1 mole each of lead and 2 moles of bromide ion. Not bromine, but iron, bromide ion. So, so this is RTP. RTP would be 24 decimeter cube. STP would be, which is 12 in the formula, and STP would be 11.2. Okay. Current of 1 amps. Now these are the questions. That's how it is. Sorry, I'm really bad in shape, out of shape. I'm just, my employment schedule is super hectic, and I'm not able to release videos as consistently as I'd like to. The traveling time's very exhaustive. Traveling 3 cities past is very exhaustive. Thank you very much. I hope you understand.